Certificados que me han preguntado.
Okay, welcome everyone to the very last talk of the school. For this we have invited Diego Blas, who is a ultra well-known, renowned, world-famous cosmologist, astroparticle physicist, and
a singer.
Beautiful person. And yeah, so he's going to be giving the closing lecture. Yeah. Besides that, well, I will tell you tomorrow, for those of you who are coming to La Palma, a few instructions, and also for those of you who don't have the certificate yet, I will also. But anyways, so the important thing is Diego and his talk.
Thank you.
So please go ahead.
Well, thanks a lot. Well, thanks for inviting me. It has been a pleasure to be around. Unfortunately, I'm giving the last talk in the sense that if you have any questions about this, we don't have more than a couple of days. I'm here until Sunday, and tomorrow I'm going to be working, so if anyone is around, yeah. Giving a closing lecture for such a rich program is, of course, a big challenge. And I was very ambitious at the beginning. I was going through all the slides, trying to summarize everything. Eventually, that was impossible. So what I'm going to do is I'm going to give you a kind of flavor or kind of the things that are maybe well, I think are really important from this school, and then some ideas that are not so well represented in the lectures that I've seen and that excite me today. So it's kind of a personal vision. Well, first, putting together the amazing amount of expertise and high-level scientists that you had this week, already with this, I think you could fill a whole library with the amount of things that you learn. So you learn from fundamental aspects of how to describe nature to the most observational part. I think that you should be very grateful to what has happened these couple of weeks. And well, we're going to come back to this in a second, but also very important, these two guys that, by the way, they like to dress very similar for formal events. Yeah, I think they had done an amazing job. Also, of course, I wanted to put this picture with the director of the institute because, yeah, there has been a lot of support, and I think the hope of the institute is that you come back now as to do real science. Now well, of course, here there are the tutors. I'm sorry, who were also very important. When I've been very lucky to have been discussing this school with the guys from the beginning. The idea was always to build a kind of community across the different topics that the Institute can offer, and also emphasizing the fundamental physics part of it. So you are this experiment. I did this experiment with also Vitor in 2017 with Lisa, and it was a full success. Like now, 5 years later, this school that we organized has generated incredible science. And I think that you guys, you have to keep patient, but I'm sure that in 3-4 years, you'll see that there has been something really special going on here. So big thanks. So let me go a bit now to the more like philosophical, or you want to call it a strategical part of my talk. And if you really think why you started to do physics, and what is physics, and what is astrophysics, and what is cosmology, and what are we here, why don't you go to a bank and get more money? There are things that really excite you, right? Like we want to understand nature. And there are many ways to address this question. You can be a pure theorist. You can really like observations. You can really like data analysis. You can like coding. That may be part of phenomenology. You can just be well, just no. I mean, you may be doing instruments, right, that really go deeper and deeper into the universe. But certainly, all these are just pieces of information. Now, imagine that we have these observations. No, there is something here, something here, something here. What observers are going to do? Well, you're going to try to keep accumulating more data. But for this, you're going to take the most, in principle, clean directions you can imagine, which to me would be these ones, right? And then you accumulate a bit more of data, and then it's when the theorists and the phenomenologists come and say, well, look, if this is a body, there should be a head, right? This is what we call naturalness argument. If all bodies in the universe have a head, and you start to see a body, then why go and look? I mean, stop maybe looking here, go and look here because there should be a head, and we're going to understand something deep. And even more important, oops, this is unstable, right? I mean, this body, you kick it, it will fall. So there seems to be a problem with the stability of this observation. So why don't you observers start to go in this direction and then finally discover the whole beauty of what was behind these observations, which at the beginning were kind of diverse, okay? So I think that, again, it's totally fine to be in your comfort zone, do your work, do it the best you can, right? When you finish your PhD, you have to be the best at something, okay? This is I think, a good message. So, you are gonna be learning a technique or something for which you're gonna be the world expert. But don't forget that you are part of something bigger. In particular, with this school, you have most likely talked to people who have another way to see physics, and don't lose this. I think that's very important. Okay, so what is astrophysics? So since we had the great pleasure to have Longer here for a while, Selovich was one of his mentors, and he's very famous for saying many things, but one of them that we have the universe as the poor man accelerator, in the sense that we want to look for new physics in astrophysics because we have already one starting point as compared to LHC, right? In LHC, they have to spend money, build the collider, and then they will place the experiments. Now here you have to build the telescopes, build LISA, build whatever, but at least you have already the conditions that are there to prove fundamental physics. And this was one of the main, you think about it, one of the main things that you have been doing in this school, understanding these conditions, right? You have been, your lecturer has been trying to do is to teach you how the universe produces high energy neutrinos, how does the universe produce gravitational waves, how do they produce light, right? And with this, now it's up to you to start building up how do we get fundamental information from that. So I'm gonna do recaps, like fast recaps, not for each particular topic, but since the one of your first module was precisely particle physics on a leg, it was very good for my analogy of this, but I'm not gonna go one by one. Theory recap. Again, a kind of a message to people who are, to you guys whose minds now are completely empty of energy after all this information. So my take on theory, I'm a theorist, but certainly I don't understand everything that you have been learning these days. Do you need to understand all this? I think you don't need to understand all this, but you have to appreciate it and to see it at a starting point, all right? To see it at a starting point of things that are gonna help you ask questions, are gonna help you, getting deeper into what fundamental issues there are nowadays and how do you address them. So you cannot be, that's my opinion, you cannot be a cosmologist or an astroparticle physicist and be completely ignorant about how particles interact. It doesn't make any sense. If you think about it, it should be the opposite. You should be fascinated by this, you see. And do you need to remember what unitarity means in particular? No, I think to me, this is not the main thing, but this is a kind of body of knowledge that you have been exposed to, so you more or less know what is known, you know what is new, you know where are some of the cracks, right? And the most important thing, when you want to answer a question, you know the phone call of someone who can help you, all right? That's what you have learned. You have learned that there are these fantastic lecturers around, that they are very nice people, and you have your colleagues now around, and if you have a question, go and ask them, but don't say, oh no, that's too difficult for me, or that's, yeah, I think that for us as physicists, that's where you're gonna really enjoy your career in the future. Of course, this is a personal view. You can do whatever you want. And also, I want to emphasize that you know a lot. So I think all of us are constantly experiencing a humbling, well, not all of us. There are people who has big egos in our community. That's absolutely true. But many of us, we are constantly having imposter syndromes. We are constantly having the feeling that we don't understand. That's absolutely normal, I think. It's part of the research experience, right? Being, questioning yourself. You know a lot already. You see, the fact that you can understand what the universe is made of, all right? And what a galaxy is made of, what drives supernova explosions, or whatever you picked as the most exciting thing during these lectures, it's amazing, all right? So whenever you question a bit yourself, think where you stand. You are really at a very high level, and you have time to learn. That's very important. As students, and in particular in your first postdoc, I think is the time where you really have time to learn. You can fail. There's no problem with that. So be patient and take all these theoretical. I just put some random, well, not random things that I think are important that are from your lectures into this circle. Of course, there are many more. But again, if you ask me now any of this in depth, I'm sure I will fail an exam, right? But the thing is that I know they exist. I know where to look for them. And we are all confused, so that's very important. So for instance, you think about the theoretical landscape, there is the standard model of particle physics, a very solid starting point. It has its cracks, okay? It's not so solid. It was not clear that the structure of the standard model is what it is. And these people were betting for other structures. Okay, this SU3, SU2, closer to 1, I mean, when people started to think about it, they thought it was ugly, but then it is what it is. So when you think about extra models, new models, people are having the same kind of attitude. So you go, again, as a astroparticle physicist or as a data analysis or as someone who do more like stuff, it's good to understand that the theories around you, they are trying to find ways to understand nature better, and it is our responsibility to come together and probe these things, okay? And they are not hard things. I mean, also as a theorist, you shouldn't go and talk to your colleagues in terms of, I don't know, representation of worlds, whatever, algebra, whatever. This doesn't make any. I think we have to also distill which part of all this landscape of theories one can then funnel towards experiments, right? That's my career also. I started as a very theoretical person, and where I really enjoyed myself is when I managed to say, oh, wait a minute, this can be measured. And now we start talking, okay? I think that you also, this is one of the targets of this school. That was my theory recap, okay? As I say, you see, I'm not gonna go through all the things you saw, just some messages. Very important nowadays is the multi-messenger attitude, all right? And you can see it in this school. Okay? You can see that light is an amazing messenger. Light is produced by many processes in the universe, but not all of them, right? So we have other messengers, cosmic rays, neutrinos, gravitational waves. Dark matter can also be a messenger once you manage to detect it, right? And all of them are bringing complementary information about the universe. Again, my target with this talk is that when you see my slides, not today, but tomorrow or whatever you go back to them, then they trigger you the curiosity to go back to one of your modules. Okay, just, oh yeah, how was these neutrinos? Which kind of information were they bringing from the universe? Which kind of processes produce them? All right. You see, all these guys have very common elements. They are emitted at some point. They travel in a medium, and then you detect them. And with this, you can ask for all these messengers the kind of same questions. What creates them? For instance, if you think about the CMB, what creates these perturbations in the sky, then you go back to inflationary models, to models of the early universe. But if you think about, for instance, gravitational waves, what creates them? So they were created by these huge collisions of black holes or something else. Right, so we're going to learn something about the emission process, but they are also, well, with some properties, they are also messengers or whatever is between us and the emitter. Yeah, you think about gravitational waves, for instance. If we ever detect those emitted from inflation, they have been seeing all the universe and in eras that we had no idea what was going on. And also cosmic rays. No? We know that because of the cosmic rays, we can put bounds on the magnetic field of the galaxy, right? With the neutrinos. The same as they propagate, also they can interact with the medium. There is all kind of physics you can learn. Well, I put Nobel Prizes where I think there are. I don't think there is. Maybe I'm wrong, but is there a Nobel Prize for cosmic rays? Yeah, maybe yes. The first detection. Yeah. So, anyways, for that matter, we are not there yet. And very important also for each of these messengers, there is the multiband aspect. Okay, multiband aspect. What do I mean? Well, if I don't tell you what this is, maybe I should have started with this. Sorry. This is the Milky Way in the visible. So the visible part of the spectrum is great, but is absorbed very, very easily by dust. You see? So you look at the Milky Way in this band, there are many things you cannot see. Instead of radio, in radio band, you see the galaxy is way more homogeneous, and also the radio is produced by synchrotrons, so you may see other processes by not only seeing one messenger, but seeing this messenger in the multiband perspective. And the most crazy stuff, well, not most crazy, but it's really crazy when you see the Milky Way in the X-rays. See that there is this huge structure here, where as I said, you could look at the galaxy for billions of years with the best optical telescope. You would never see because this corresponds to other kind of physics, right? So again, these messengers that you have been taught about during these 2 weeks, they also come in a variety of colors, if you want. So it is also important that you go back to those. The next thing I want to recap is the taxonomy of objects for fundamental physics. Again, you think about the school and you put it together in length of the observer, of the observation. You can start with the biggest thing you can see in a sense is the Big Bang nucleosynthesis observations. CMB, large-scale structure, intergalactic medium, galactic cluster, AGN, all those, all those are very complex astrophysical objects, right? So it's very important that you get first the standard picture. So they are, take the CMB, no, which is a very clean observable. It's very clean because the kind of physics that is behind is classical physics also. So it's something that people have fought to understand for a long time. But eventually, the process that I think we have to take is a exploratory one. This is Rainer Bayes, the guy who invented LIGO, and this is Amundsen, and this is Scott, the guys who went first to the South Pole. Okay, yeah, I like to put this picture just to send this to compare these pioneers. No, some of them just trying to get totally out of the box and ideas. How do we go beyond in this exploration beyond the standard law? I think it's very important that, and this is something we have been discussing with Jorge and with other people, it's very important to get the standard picture to be able to define clean observables. A clean observable, what I mean by that, is something that where you can marginalize the astrophysics. If the astrophysics is all over the place, it's very hard to get fundamental physics, right? So, what does it mean that all the astrophysical observables are equally dirty? No, some of them, there are good examples that I could have given you, but some of the observables may be very, very clean for astrophysics. So you change a bit your astrophysical parameters, nothing changes. And if you add a new channel of new physics, something happens. One of them, well, just the mass of the neutron stars, for instance, in standard physics is relatively well determined. If you suddenly see a neutron star of 3 solar masses, there is something wrong. Okay, but maybe that's not the best example. But the cooling of stars is something that, for instance, people believe is a clean observable. Or in all these observations, if you go back to your notes, you realize that what the lecturers were trying to do is to first give you the standard picture, as Ekfir did, or the the also Francesca or the people giving you what is the standard picture in the standard model, this one. Okay, maybe now let me see which particular property is very robust, and then when I do new physics, it will be changed. And for this, again, you need to understand the fundamental, the fundamental physics before you start doing anything crazy, right? I think that's very important. In particular, because the most challenging part of our job to do fundamental physics with astrophysics is this one. Okay, I think it's the crux of our life. In the end, there will be many parameters in our models, and we need to understand which of them are not degenerate with the new physics. Okay. A way to go is to do cross correlation. So that's very important. That since you know already all these possible observations, now it is our job also to, once you believe in some new particle, once you believe in some new physics, to go one by one and see if there is a kind of, cross correlation between them you can use. Okay, for instance, if there is a particular structure in the sky that you think is gonna do something to a CMB, maybe it also does something to the intergalactic medium, and so on and so forth. So this takes me to the last list I have, okay, which is the list of open questions. There are many ways to classify this: fundamental, observational. I'm gonna mainly discuss the fundamental ones, and this is something that you can take home for your future. You can add some of them. Maybe one can do a school open questions webpage or something, okay? Because you can for sure rescue more of them from the notes. In all of these messengers, there are open questions. You can start with the neutrinos. For instance, the mass of the neutrino is unknown, is the last parameter missing in the PDG. At some point, it will be measured. But even when it's measured, its value is very different from other scales in the standard model. So it's very strange. So I think, and again, if you are doing neutrino cosmology, as I said, I think you have to understand that you are probing maybe important also for which kind of mechanisms, which kind of physics beyond the standard model is behind this neutrino mass. So you are not only running your code, you have to also go and put your physics into context. Also, the flavor structure that I don't know it was discussed that much. So, for instance, why these families they have some particular different properties, and neutrinos interact very weakly in weird ways that may be probed by cosmology or astrophysics. That's something that Olga was telling you today. Also, within the standard model, you learn from Valerie that there is this baryonic asymmetry in the universe that, in principle, is not very natural. So you need a process to generate the amount of baryons that we see today. The problem with baryogenesis normally is that until today, it was a very hard topic because there are many models that can produce the observed baryonic asymmetry, and there is only one single observation, which is the number of baryons per photon. Okay. This changed with gravitational waves. Okay. With gravitational waves, some of these models precisely generate a signal in LISA, and that's why, as I will discuss in other transparencies, this cross correlation of signals in the field of early universe is really blooming, exploding these days. Okay, let's move a bit faster. Dark matter. In dark matter, we don't know anything about the fundamental properties. We don't know the mass. We don't know if it is a particle, if it is a wave. We don't know the spin. We don't know how it is produced. We don't know how does it interact. We don't know how to feel it locally. There is a extremely worrisome scenario where we will never learn anything about this. But as you learned today from Vitor, who told you, I think no one could ever imagine that you could detect, that you could say robustly that the mass of the dark matter cannot be 10 to the minus 18. I think you asked this question, I don't know, 10 years ago, well, maybe 12. The answer was, we will never learn this. And now, precisely because of this connection between theory and observation, so the plots that Vitor was giving today to you, they are done by people who are really understanding the observations, right? So there is this connection that has managed to make this miracle happen, right? In the dark energy, we hope something like this happens in the future. So we are still lacking a lot of information about what dark energy is. I think that the progress in dark energy has been maybe the most frustrating one, because there, as compared to what we knew in '97, when people discovered that lambda CDM had a lambda, there has not been so much progress. People expect that with Euclid, with the new observations, we could learn something maybe about dark energy. But it's true that here in dark energy, as Weinberg said, is really the throat in the bone of the field. But at some point, maybe we'll get something of phenomenology, is that you expect your quantum gravity theory to be very much affecting only very small scales. But that's not true. I mean, there are quantum gravity models that percolate, until very low energy. So in principle, it's always good to keep your eyes open to whatever you do in terms of gravity, if they can give you some new insight of what quantum gravity can be. Can we modify gravity for a good purpose? By this I mean, can we help these problems by modifying gravity? Maybe not. Are we seeing black holes? So there are many questions that I think you have been asking to your lecturers during this week, that the lecturers have been also asking you, and whose answers are still out there. In the observational, it's not my cup of tea, so I let you fill this gap, yourselves. Okay, so that was half of my talk. Now, are we living in boring times? I think that some fields are living boring times, unfortunately. We are not there. Okay, I think that as astroparticle, astrophysics, cosmology, fundamental physics, this merging is living maybe too exciting times, in the sense that it's even hard to distill what is important and what is not. I'm going to give you an example, a counterexample of this, and also to address another point that you have normally when you do your PhD, is that you see all this amount of science that was done before you, and you feel a bit humble and say, oh, my contribution is going to be nothing because everything has been done. What can I do with my code? What can I do with my equations? Well, take one example. Okay, gravitational waves and dark matter. All right? You can ask yourself today or 20 years ago, what is the connection between these two fields? Well, a way to answer what is the interest of the community on this and what is the progress on this question is by going to a repository and look for abstracts with both gravitational waves and dark matter. And you see that there was some interest, but suddenly, during your lifetime, okay, when you started university, I don't know, you're too young, but maybe this way, boom. This is happening now. What does it mean? That it's now that a question as fundamental as how much can I learn about dark matter from gravitational wave observation, it is now that this is being asked. And like this, I'm sure you can look for many other questions. So the reason between this is kind of common to other astrophysics. Something happened, okay, like Virgo for detection. So the community suddenly believes these crazy guys that have been doing this for 20 years or 30. Also, LISA gets approved. Okay, of course there is a correlation. So 2015, well, the detection, 16, the announcement, 2017, and also what I would call a dark sector fever. Around these times, they turn on the LHC, they don't see supersymmetry, they don't see new particles, or maybe the dark matter is not a WIMP. Okay, we were obsessed with the WIMP. So people were asking this question, gravitational waves and dark matter, within the WIMP scenario. As soon as you open it, you see, people started to realize that there are so many ways in which the dark sector and gravitational waves can interact. correct? And this is happening. I use this also. It's my example because I work on this, but it's to show that data in all these possible messengers is getting better to levels that certainly allow you to find new questions. Well, the questions were always there, but now the answers are completely different. Okay, and in particular in this case, LISA and also interferometric atomic interferometers are also getting really. It's something that is happening now. Okay. I like to say this. Yeah, as this is a closing lecture and everyone is very tired. Instead of equations, I put pictures. So I don't know who this guy is, but he's a guy who went to the west in the gold rush. And when you see an opportunity, you can try and pretend to be one of miner, or I don't know how they are called, gold rushers. So one of these people who are gonna look for something in the data, something that I'm not gonna think. I'm just gonna go and do whatever everyone is doing. Instead, this guy became rich. Why? This guy is Levi Strauss. Okay, Levi Strauss. He was selling the trousers to these guys. Okay, so he saw the opportunity there. He kind of went outside because, well, I have time, no? I could never beat Olga, but I'm trying to at least be a bit funny. Okay, he used jeans first for sales. This kind of textile material. He was trying, and it didn't work. But then he realized that he could use it for trousers that these guys were wearing. What I want to say with that is, of course, not that you become a filthy capitalist, but that you think about opportunities where you are looking at the data. And for this, again, think about all you have learned in this school, think about all the connections you have made, and ask the question that is really at the top of your capacities, okay? Not just go there and try to hunt for things in the data, okay? So go back to this amazing people, and I think all of them will be very happy to answer your questions, right? I think also the organizers were very careful not to bring. I mean, let me put it on the positive. So to bring great people who are very much willing to go and interact with you guys. Anything else? Also, when had you learned everything that is there? Of course not. Not there. It's amazing that you go for in the list of topics that this is a slide from David, and you have gone all the way. You have explored everything in this Big Bang picture. Okay, and here, of course, there are many things that are even galaxies or intergalactic medium. So you have gone an amazing road, but there are things that are missing. Of course, this is because it's 2 weeks. Otherwise, you have to come here and live here, and that are very much evolving these days. So one of them, I think, is AI-informed physics. I didn't want to use machine learning. I think that this is also my prejudice. The way the machine can be used to understand things is very broad. So you can't just take data and try to train the chains to filter out your data and get a better prediction of something. But I very much believe that there are also questions that, again, if you ask them properly, the machine may help you to solve for it. One of the particular questions is that trying to solve very complex differential equations. So you are doing it with some discretization method and then interpolations. So maybe the machine can do it better. But this is a question that I think you have to ask. It's not, it's not only machine learning. It's really trying to use the machine to do some what I call informed physics. But again, this is not at all my field, but just for exciting things that are out there. One of them that is more in the astro, and that we have experts here, but of course, it could not fit the 2 weeks, is stars as laboratories of fundamental physics. You can imagine that the stars have very dense media sometimes. They can be as energetic as pulsars. And all of this has been used, and is being used by people like us to learn about dark matter, about neutrinos, about new particles, also about the Standard Model. For instance, how it's amazing that you think about it, the density of neutron stars is one of the few places where you really can probe QCD in some ranges of parameters that no experiment can really do. Well, there are some attempts at CERN, but stars can teach you what quarks like to do when they are condensed. Okay. And finally, this is going to be the rest of my talk: the precision frontier, which is where I'm is more my cup of tea. So, what do I mean by the precision frontier? Well, this is going to be something completely different. Let me give you two examples: a precision frontier in the lab, precision frontier in astrophysics. This is a relatively well-known plot of the relative uncertainty in the determination of a transition in a particular atom. Well, those are like different transitions, the cesium clocks, okay, which is a megahertz transition, and this is an optical transition. And as a function of time, the progress in the precision of this has been amazing. Well, I guess you heard about this, but this is the way to probe it. That nowadays the fractional uncertainty in the transitions is at the order of 10 to the minus 18 in the optical. And you see this amazing progress also happening in the optical case. It took a while to understand how to do it, and once they did it, bam. Another one you can use, another way to emphasize the progress in the precision frontier is the lifetime of some entangled states, some qubits, as a function of time. So in this case, we have not even spanned 20 years, and we have 7 orders of magnitude in the amount of time that these guys take to decohere, so that these guys really keep their quantum properties. Okay, so we are certainly in an era that, as physicists, we should be aware that our colleagues in the lab next to us are doing these things. Then it's up to you to ignore it, or to just say, well, look, this is amazing. Can we do something together? Another place where precision has amazing numbers is in the tracking of pulsars. So pulsars are neutron stars that are characterized by having a beam, okay, going through an axis which is not aligned with the rotation axis. That means that as they rotate, some of them, every rotation, point their beam towards us. And then you can measure this rotation period with a very high accuracy. So high as this one. I think that's one of the most precise ones. I don't know how many numbers, maybe 15, I don't know, 12. So this particular pulsar, which has a mass similar to the sun, rotates 5,000 times or whatever, 1,000 times per second. And we can measure this with this amazing precision. But not only that, they are also in binary systems. And since as you are in a binary system, sometimes you are farther away from me, sometimes you are closer away from me, this also generates some changes in the time of arrival of this signal, right? So imagine that this guy is a bit farther or closer in an orbital motion, then your tracking of this will be a bit modified by the orbital motion. And this period, for instance, the period of the binary, the time dependence of the period of binaries, which are of the order of days, is now also with 12 decimals. So this is an amazing observation, right? So we are living in these times, precision physics. But think about it. We have this precision technology, this precision measurement, and at the same time, we live here. We have been very lucky that the universe has created a lot of backgrounds that are going through your very precise detectors, right? Of course, you can try to isolate your stuff. Sometimes it's going to be impossible. So there is, of course, light coming from all over the universe. But there are also cosmic neutrinos generated way before the Big Bang, okay, when the elements were formed, and they are gonna travel all over the universe, and now they're gonna be somewhere. There is like 50 neutrinos here now. From the in a centimeter cube, there is more or less like 56. Okay, fundamental neutrinos. 56 is nothing, right? If you compare to Avogadro number, 56 is nothing, but they are there, right? So now, how do we detect them? Well, but also gravitational waves. They're going to be all over produced all over the universe, maybe at the beginning, maybe later on. Dark matter, all this is permeating the universe, and this is the real picture. So your labs are full of them, and your astrophysics are full of this background. So you cannot live without them. So instead of being a source of noise, now the philosophy of this precision frontier is turning this around. If this is the accuracy at which I can detect something, what can I say about these fundamental backgrounds, which in principle are going to decohere my quantum state, are going to certainly maybe modify a bit the orbital motion of these guys, or the time that the signal takes to arrive to me, right? So this is, I think, one of the things that excites me more these days, trying to precisely use this precision frontier in different aspects to learn about fundamental physics. Now, the questions are typically very simple. For instance, how does an atomic clock feel the dark matter? So I was thinking about this for 2 years, and I was really frustrated because it was not it was totally beyond my comfort, okay? But then what I did, well, I did what I'm telling you to do. So I started to discuss with everyone. No one cared until I found well, let me go. I go for a couple of gentlemen, Rodrigo Alonso and Peter Wolf, who we started to discuss, and eventually we realized that this was not such a difficult problem to start with, because the question was so well formed, so well posed, that we could really make progress on this. And now I go back and tell you why can't this be relevant for dark matter searches. All right. So in the dark matter searches, there is a big problem with the standard searches. How does the standard search work? I think you saw it. At least I heard that Olga mentioned it before, but I guess you also saw it in Tracy's. Yeah, Tracy also mentioned this, right? So the dark matter arrives, it scatters with a whatever, and then this generates a recoil, so it transfers momentum. And then what you measure is the nucleus or whatever. You can do it with different materials, but the most simple thing is that there is an atom, dark matter comes, and then this guy goes and generates a perturbation in the material, and this perturbation hits a bit the material, or you detect a wave. Now, if you compute the amount of energy transfer, yeah, this is in the lectures by Tracy, you can see that the maximum amount transferred by the standard dark matter in the halo is given by the dark matter mass divided by GeV and then kilo electron volts. So what does it mean? That if the dark matter is light, the amount of energy that you put in the detector is also very small. What does it mean? That if you are below kilo electron volts, all the detectors fail to detect this interaction. No matter, I mean, dark matter could be an elephant. Okay, it could be, well, not a light elephant. It could be anything that interacted strongly, as strongly as you want, but you would never see anything in these cases. That's why the cross section that you can constrain with the direct detection goes, loses a lot of sensitivity at low masses, because there is nothing you can detect, right? Because you don't transfer enough momentum to the material. So how do we solve this? How do we solve? This is a big thing for dark matter searches. Quantum mechanics here comes to the rescue for the following reason. My aim is not that you understand this in detail, but at least that you understand the flavor of how do we answer this question. An atomic clock, again, when you think about it for the first time as a theorist, you have no idea where to start. Then it turns out that Stephen Weinberg has a very nice summary in his book. So once we found this, everything was simpler. It works in the following way. There is an atom, which is there in a quantum state, again, something that we know more or less how to describe, then this atom, it is interacting with light for a small period of time, and this generates a superposition of two states. Okay, but when you kind of excite it a little bit, it eventually turns into the ground state plus excited state. And then there is a very well studied process of eventually measuring the final amount of these guys in the excited state and the final amount of guys in the initial state. All right, again, I'm not claiming, I mean, you shouldn't understand. If you understand this from this, you are way beyond me. Okay, this is what is called Ramsey sequence. And if you want to understand it, this is the way to go. Now, what is amazing is that when you tune well these times, the time at which you shine the light, the time at which this guy is flying freely, and the time at which you shine the light again, there is a particular combination for which the amount of states, let's say the probability that you are in state 2 is very simple. It's given by the difference between the energy of the state 2 minus the state 1 minus the frequency of the light that you are shining. Why this is great? Why this is robust? Because then what people do is to try to find delta omega equals 0. So they try to find so they play with this omega, okay? And when they find that delta omega is equal to 0, they know that omega is equal to this transition. So that's the way they lock the frequency of this apparatus to the transition frequency of the states. And since it is a maximum, it's very robust. So you don't care if you lose something. You can really, change in omega, try to find the maximum of this probability, and that would be at omega equal to this transition. Okay. Now, this is not real life. Real life is this. Okay. Real life has dark matter coming in, interacting with this atom, dark matter coming in, interacting with this atom. Doesn't matter how it works, but when you interact with an atom, you are modifying its time evolution. So while it is evolving in this big time, it is not freely just evolving with the eigenvalue of the energy, something that is on your quantum mechanics one. It is something that is more complicated, okay? But that, eventually you can forget about this formula. I don't want to show off. I want to say that eventually, putting together all this knowledge, we manage to understand what happens. And what happens is that the energy are kind of shifted, the energy of one and energy two are kind of shifted to the level, okay, that you can understand how an atomic clock feels the dark matter. All right, and this required, again, a quantum physicist who care nothing about dark matter, a phenomenologist, and myself, right? And again, it was a very interesting process. It took a couple of years just to know the language, but now, for instance, this is a very powerful way to look for dark matter. All right, so just to give you an example of how we answer this question. Okay, so another, I checked your transparencies, and there is something that I wanted to tell you, but I don't want to take too much of your time. So one of the things that were discussed in your lectures is ultralight dark matter. It was discussed by Kfir, it was discussed by other people, and I'm now realizing that I put it here because then I wanted to tell you how does it modify an atomic clock. But maybe what I'm going to do is just give you something that no one has given to you, is that why are we describing dark matter in the ultralight regime as a field as compared to as a collection of particles? I think that no one went to this point, no? In your lectures. Okay, so why do you describe this light with Maxwell's equations and not as, as a collection of quanta that comes to your... Okay, this is a question that you can pose to any quantum field theory. So when do you get a classical limit? When are the equations of the classical field theory enough to describe the process? And the answer is known, is when the occupation number of the levels is big and they have random phases. So when basically you have many photons and they don't form a condensate. They are just produced randomly by the electrons in the filaments of the bulb or whatever. So whenever there is high occupation numbers and of random phases, then a classical field theory is enough. You don't need to care about quantum field theory. All right? Now, when does this happen with dark matter? So this is a galaxy for me. Okay, a galaxy is a cube of a certain size and a certain size in momentum. So you have the dark matter particles in the galaxy. They are confined to 100 kiloparsecs for the Milky Way, and they are also confined in momentum space, because if they fly too fast, they will leave the galaxy. So the momentum and the position of the galaxy are finite. But if you remember, again, from your quantum mechanics, the phase space is also finite. That means that if this whole volume is divided into small cells, and each cell has a size which is h bar, okay, the quantum Planck scale. Okay, this is again something that is in your quantum mechanics background. It should be. So with this, you can try to learn how many states are available in this volume. So how many of these small states are there? And for the Milky Way, this is what I get. Why there is the mass here? Because you know the maximum velocity, but the maximum momentum depends on the mass, right? So it's basically this cube, and then divided by h bar. Cube also. And the number of states that you can fit in the Milky Way depends on the mass of the particle, right? And this is the number I get. Of course, this number is order of magnitude. How do I know if I have these states occupied by more than one particle? So with these states, you have to explain all the mass of the Milky Way. So if you multiply ns by m, by the mass of the states, okay, ns multiplied by m, if you get something bigger than the mass of the Milky Way, then you don't need to populate all of them. You can just populate some of them. If you get that ns multiplying by the mass is smaller than the mass of the Milky Way, you need to put more than one particle per state. Is this clear? Total number of states multiplying the mass, okay, and then multiplying by the total, so by the occupation number of each state should give you the mass of the Milky Way. Well, again, you will have this available. And if you put this number, when this is bigger than 1, that means that the dark matter has to have, this model of dark matter requires that for each state you put more than one particle, and when it is smaller than 1, these dark matter models live freely with occupation numbers smaller than 1. So from this you see that the frontier is around the EV. So wherever things are below electron volt, in the dark matter landscape, you can use you should use the particle description, because you are really talking about particles but when the mass is below electron volts, well, up to a factor, then you have to use classical field theory. And here is the question also. This is also telling you a very important thing. You cannot have fermionic dark matter below a certain mass, okay? Because precisely you cannot. I mean, really, you should. If dark matter were fermions, you would be trying to put new states on states which are already occupied, and that would generate a halo that would really expand. Okay, that's why the mass of the fermionic dark matter can never be below. If you do this number properly, it's below kilo electron volt, more or less. All right. So then, which kind of equations do you use? Well, if it is a simple scalar field, then you have to use waves of these guys. And again, I came back to this point because I saw that in the slides it was very fast, and I think it's beautiful to see this connection. It's a bit similar to what Vitor was saying this morning. No? This is a very beautiful connection of quantum mechanics and galactic dynamics. You see? How do you were saying we can connect black hole physics with particle physics. Here I'm connected galactic dynamics with the fundamental quantum properties of dark matter, right? So it's very beautiful. And I'm going to skip this a little bit. And just telling you that with these ideas of this dark matter, how does it affect atomic clocks, we were able to beat in some models the bounds from other guys by a lot. Okay? Then these models are not the best, and that's why eventually, you have to maybe look for something else. But the idea is that we had this question, we worked together, and we managed to find the answer. How do pulsar signals feel dark matter? So remember that I'm in this precision obsession, right? And normally this is the way I am for some time. And in this case, I have to think what to do, because I don't want to also spend too much time. My question was, again, my fundamental, the place where I'm coming from is, I have this very precise frontier of pulsars and also of atomic clocks and stuff, and which kind of signals of the universe I can feel. So in principle, I can also ask how do they feel dark matter and how do they feel gravitational waves. So what I'm going to do is I'm going to focus only on the dark matter scene, because otherwise it's going to be too long, and I see that this is already cooling off a bit. And I will put the slides with all the information, right? So that you can go through it a little bit, all right? I think that's the most. So for what I was doing now, I was giving a kind of complementary picture of gravitational waves as compared to what was given by Vitor, but okay, it will be on the slides now. Coming back to what you have learned in this week, how can pulsars feel dark matter? Well, pulsars, they are traveling also in the dark matter field. What you learn from Kfir is that if you are traveling, remember he was put in a globular cluster, traveling in a medium of dark matter, and he was finding that there is a friction. You generate a wake behind you, a friction called dynamical friction that slows you down a little bit. So pulsars in a dark matter field, they tend to slow down, right? Can you measure this? Well, people have explored this in some detail. But also, the pulsar is traveling in a medium, and this medium is oscillating, okay? If it has this wavy behavior, okay? So this can also transfer energy from in this case, you transfer energy from the pulsar into the medium. In this case, you transfer energy from the medium into the system. So there is a kind of dynamics in which, by living in a medium, you can either lose energy, but you can also get energy out of it. So by exploring this, so forget about this picture because this has to do with the gravitational wave. By exploring this precise question, we managed to understand how the pulsar period, the binary period, is changing, right, for different dark matter models, all right, as a function of the dark matter profile. So this is a dark matter profile with certain density, right? And this would be the signal that I see in the pulsar. Unfortunately, you remember I was giving you numbers of this guy of 10 to the minus 12, so we cannot observe this directly, but it was very fun to do this exercise and realize that, well, eventually we are not there, but certainly there is an effect that is there, and it was fun to discover. And finally, and I will finish with this, there's another way in which pulsars can feel the dark matter of the gravitational waves. Remember that we have a radio wave coming to us, all right? And as it comes to us, it is seeing the dark matter medium. So maybe it is absorbed by dark matter. Okay, maybe it is absorbed by gravitational waves in between. But also what can happen is that maybe the signal, as it travels, we know it so well that some of these properties, like its polarization, its frequency, even its speed, the speed of propagation, are modified. And with Jorge, Andres and Jorge, that you know well after this week, we had a paper this year, where we managed to precisely use the very well established polarization of the light from the pulsars and other observations from here, from Canary Islands, to constrain the possibility that in the middle there is a oscillating dark matter that would change its polarization. Again, these are examples where I think the most important thing for here is coming back to my more philosophical message, is that you identify the question. The question is always, in our case, always very clean. Okay, you think about it, it's like, there is this dark matter that is oscillating, and I have all this data of polarization, which is great. There should be something here. Or we have these binaries which are moving with this amazing precision, and there is a dark matter medium which is stopping this motion. So how do I get and go and compute this? Okay, I'm gonna also skip this. And this is my last message. How do we unveil the mysteries of the universe? Okay, remember that this is, at least this is my motivation. So why, you can also put it in the different language. Why don't you go and work in a bank? Okay, because we are excited about this. Okay, maybe now we are very tired, but in the end, we have to feel that privilege, no, for two reasons. First, that we are being paid to do this, and second, that we are living in a time where our field is really expanding. So where the amount of information, the amount of connections with theory are being made right now. Okay, so please go back to this list of things that I wrote in the slides. Go back to your to the slides that are on Indico. Don't give up, in the sense that if something is very hard because it's not in your comfort zone, I think that it doesn't make sense to give up. You just have it there. You know, you can study if you need it, but again, don't say, oh no, this is nothing to do with me. I can tell this from my own experience regarding data analysis, right? That it was hard for me to always go back, and I'm very happy to work with people that were very patient to teach me. And then eventually this allows you to get the general picture of how to make progress. Okay, so get help, get excited, and remember that eventually, at least to me, there is this global picture that we get only if we connect to our colleagues and if we leave our comfort zone. I made this cloud of words with the list I had before. I don't know why the more valued one was mass. So a massive clap to our organizers. Thank you very much.
So thank you, Diego. I don't know if anyone wants to add anything or have any questions for Diego.
Hello, thank you very much for the overview. It was very nice. I really liked your analogy with a statue. And I would like to ask you, I don't know if this is easy to answer, what percentage of the statue do you think that we have uncovered? And do you think that all these pieces of knowledge that we've seen this week, do they all come from the same portion of the statue, or are they somehow disconnected pieces that we're trying to connect? What's your view on this?
Right. Indeed, I must confess, I stole this idea, okay, from a friend of us, Javier Redondo, who works on action physics. Okay, and the way he shows the statue is by precisely trying to do an energy direction here. So what he does is that he shows first the leg, and then he goes up, and then precisely he said, no, but wait a minute, there is also a low energy. There's a new low energy leg that we have not explored. I think, and when we think about the way we are exploring, we are typically biased by different things. And in the case of fundamental physics, For instance, because of the way the progress of particle physics have progressed, there was a huge effort into going to high energy, for instance, right? And this eventually generated a huge amount of progress. But for instance, nowadays people are focusing on the low, what they call low intensity on this precision frontier. So the frontier of precision, I think, is a frontier that we have not explored enough. And I can tell you my own experience. The typical thing is that you cannot, when you talk to people doing these atomic thingies, we don't have the same language, and that means that we have not explored this. So they don't even know how to put a gravitational wave on a qubit system, right? So from this point of view, there are some directions. By the way, I invite you also to have a look at these snow mass reports. That I don't know if you know about them, but the US community every 10 years they kind of se flagellan. They go through this process of trying to get together and produce the analysis of the state of the field. And the intensity frontier, the precision frontier, is one of those identified. Another one, naturalness. I think that naturalness, there are puzzles about the universe which we have no idea why they are there. To me, the most puzzling one is that the universe is metastable. You take the mass of the top, could be whatever, and then you talk to your field theorist, what you learn on your first lecture, and it turns out that with this particular value, with this particular standard model that we have, we are in a universe that was very close to disappear exactly when we lived. Wow, that is
in the standard model.
In the standard model, all right? Or the cosmological coincidence, the fact that so from this, I think that we are certainly missing the head. I think that naturalness. I like naturalness. Some people are giving up. I think that naturalness, but in the sense that we are naturalness. Or driven by the kind of puzzles that there are. So I think that we are maybe this way. Also, on the other hand, think about it. In the last 100 years, we have the way I put it in my proposals is that we have this global picture of 44 orders of magnitude. So we can, with the standard model, we can describe everything. So it's really, I think we have a lot. We have learned a lot, but there are still a lot of mysteries. Yeah. Yeah.
As you show us, in the recent years, the people start to work a lot in gravitational waves after they were detected. Maybe because in the past we don't believe that we can detect them. And so I wonder what happened with the graviton.
Yeah. The graviton, there is there are many ways to answer your question. Okay, so you know now when you need to talk about gravitons. You need to talk about gravitons when the occupation number is small. All right. So you take a gravitational wave. You can do the same. You can do the same thing I did here, and you can compute how many gravitons. In the end, let me go. So it's good that I eventually explain this then. Here, what I'm telling you is that the dark matter halo is made of dark matter particles, all right? And in the case where when you can compute how many of these particles there is per state, and when you have that the occupation number of the states is more than 1, then you can have a classical description. So the graviton is the quanta of gravity. So you can ask yourself, are there gravitational waves detected made of single quanta, or are they can they be described as a field theory? The answer is that they are purely classical. Okay? But this is not always going to be the case. There are some detectors that are being proposed that if they ever detect gravitational waves, they're going to detect single gravitons. Okay, they will be for gravitational waves of higher frequencies. This is a first way to answer your question. So in principle, for the kind of gravitational waves that LIGO will detect, that LISA will detect, those are like classical GR is going to give you the answer. But for those at higher frequencies, which is another frontier now of research, as you will see when you see my slides, if you do it, there is another frontier, which is high energy gravitational waves. Then there is this question that at some point you will detect single gravitons. And on the other side, if you detect gravitational waves of very, very low frequencies, so low that they are of the size, the wavelength is of the size of the horizon. Okay, so when you think about gravitational waves, okay, let me put this. So there is a map of frequency versus basically intensity. And the LIGO detectors are more or less at 100 hertz. The CMB detections, the bounds, are at 10 to the minus 17, which corresponds to gigaparsecs. Okay, you transform frequency into wavelength. So those are gravitational waves that, if they are produced, they have been produced at the scale of the horizon. There is nothing that can generate this super long wavelength if it's not inflation. So you think about now which kind of frequency which kind of wavelength I'm generating. It has to do with the frequency at which I move. So if I'm not very big, I can never generate something of big wavelength. So these huge wavelengths of these CMB gravitational wave observations, they correspond to things that are horizon size. So they can only be generated by inflation. And inflation, the way they are generated is through the quantum fluctuations that are associated with gravitons. Okay, now I close the circle. So if we ever detect, yes, to sum up, the gravitational waves detected with LIGO, they are purely classical. If we ever detect those the CMB searches are looking for, I think they can only be generated by quantum fluctuations of the gravitational field. And then there is the frontier of pushing also to so high energies that you will detect single gravitons. In the same way that you think about X-rays versus radio. When you detect radio waves, you don't think about single photons. But when you detect X-rays, it's like, bam, it's a high energy. Photons are also like single versus, yeah.
Okay.
It was an easy question.
Any more questions or comments? I don't see any. So let's thank again Diego.
Good luck.
Yes, we have come to the end of the school. So what? Yeah. No, come on. Let's do the sentimental thing before. I mean, quickly and wrap up. So thank you all for coming. I mean, it has been a wonderful experience for us as well. Very tiring, but very rewarding to see all of you coming to all the lectures every day and seeing you in the coolest place in La Laguna every night. So it's been also, I see that all of you have get to know each other, coming from very different places and all. So congratulations for making to the end and enjoying this experience. I think you are very lucky. I wish I had the opportunity to be as lucky as you have been these 2 weeks when I was a student. And yes, so that's what I wanted to say. Carlos, what do you have to say?
Easy things, I have to say the typical things. No, it was exhausting, but it's also a pleasure for us. I think it's really rewarding seeing you guys asking questions. Remember, first day, I insisted you that first the most important thing would be that you guys ask questions. I know it sounds a bit like, I'm now sounding a bit like an old guy, but I remember when I was your age, and I remember that we were all dead shy. We would hardly ask any question, raise any hand. And it's really great to see that you guys, the young guys, are improving our generation, and that you have no shyness in just asking questions, not being afraid of looking stupid or anything, which is just bullshit, right? Simply just ask questions and try to learn as much as you can. I think this was really great from you guys. It's great, as I say, to see you all having fun. I wish we we were 20 years younger.
And we hope to see you around. I mean, in all the conferences, and we are colleagues. So different generation, but yeah, we are colleagues. So yes. So if you have any questions, comments, we can. We have some more prosaic announcements to make regarding the excursion tomorrow. For those of you who are coming to the, okay, so they have our flight is leaving at 7:30, so we have to be in Plaza de la Adelantada at 6. It's half an hour before than we expected. They just told us in order to make room for everyone in the plane.
The bus won't wait, unlike
yeah.
The bus won't wait, so please don't oversleep, otherwise you will miss the flight.
Yeah. I mean, maybe it's, yeah. Sorry about that. So what else? Yeah, some of you do not have the certificates of the talks, I think. We will send them to you via email. Is that all right? Okay. What else? The talk by Malcolm Longer, the public talk, is open to everyone. You are, of course, invited to come. It's at 5:30, not at 6:30, okay? There was some confusion somewhere. So, yes, so, yeah, thank you. Yeah.
See you soon.
Yeah.